This is University of Colorado Television. Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment.
In this experiment, one can study harmonic motion and also driven harmonic motion. This cart is the oscillator. It's mounted between two springs on a glass surface. One wants to be sure that the wheels of the cart are good and clean, that wipe them off, and that the glass is clean, and also that the glass is level, both lengthwise and sideways, so that the cart as it oscillates doesn't walk one way or the other sideways. One can then study the period, measure it quite accurately using a stopwatch, and then also study the damping, to pull it out a certain distance, and then see that each time what the amplitude is at the end of each period. One can see how both the period and the damping vary with mass. One can put other masses on here and look at both the period and the mass. And of course, if the mass slips, that'll may even change the damping. One can also increase the damping by using a magnet. For example, here is a magnet which, if it's placed over here, will induce eddy currents, and the damping will be different, greater with the magnet than was without. And one can go even further by having more conductor, by adding more plates. One can make the damping even larger, so that one can study. This is not as interesting for the natural vibration, but you will want to see what the response to the forced vibration will be under various conditions of damping. In order to get the forced vibration, one uses this variable speed motor, which is quite stable, with this little power supply here. One switch is left in the on position, and this 3-position switch is used to start and stop the motor. It doesn't matter which direction it goes, forward or backward. The little crank here performs essentially the same oscillation, and one can vary the speed of that. It's now set up, and one always has to wait until the transient has died down, that is, and until this is oscillating with the frequency of the driven motion, rather than with its natural frequency. Any disturbance you make in it any change introduces a transient of the natural frequency, and you have to wait for that to die out. It's now set at 45, which is fairly near resonance. Let me change this dial a little bit. Let's move it from 45 to 48, which is a value I checked before, and you can see the kind of thing that happens. There it is set at 48. And now you can see that let's look at the cart. The amplitude is gradually beginning to build up, and it'll take quite a while when you're really at resonance until you've reached a completely stable situation. The amplitude is still building up a little bit. I'll have to wait a little while longer. And now let's see, once it's reached that stable situation, what happens if I move the dial. Let's watch that. I'll move it just a few divisions. I'll move it from 48 up to 50. And let's watch the cart again. And you can see, stop down. And clearly this is not a steady state, because it doesn't stop, it comes up again. There is the fact that this is slightly off the natural frequency, makes for a sort of beat note, which has to die out until finally I will get some sort of a steady state. But you can see it's going to take, when you're near resonance, quite a long time to make accurate readings. When you're far from resonance, you can perhaps move the frequency dial as much as 5 divisions at a time and plot the response. But when you're near resonance, you may want to move it as little as half a division of time and wait a long time between each reading. In addition to the amplitude response for different masses and different, you can in each case look at the phases. We may add an automatic device to help with that, but even as it is now, two people can very easily see the phase. If I look at this crank, one person can say now every time this reaches the left-hand side of the screen, and the other person can keep track of this, and you can see whether they move together, being out of phase, or whether they move in opposite, move like this, being in phase, or whether the phase is something in between 0 and 180 degrees, namely 90 degrees. And although you can't measure it within a few degrees, you can tell it quite easily. Now you see this has finally reached a steady state, and that the amplitude is small, even though I've only moved the dial, as you saw, a very few divisions. So to get a good curve near resonance takes great care and quite a long time. That's essentially all that's involved in this experiment, but it turns out to give very nice and versatile resonance curves.
Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television.